This module has two major components. The first one is about the concept of correlation. Most correlations are between two continuous ratio variables that are plotted against each other like this graph. Remember, a continuous variable is one that has any number of possible divisions between the values. So, like counting people is not continuous because you can't have half a person. But counting money is continuous because you can have half dollars, quarter dollars, tenth of a dollar, and almost an infinitely small valuation of divisions. Remember that a ratio variable is one that is a count variable. The distance between one number and the next number and the next is always the same distance. Like as we learned back in Module 1, the distance between 1 and 2 is the same as the distance between 5 and 6. And a ratio variable also has a true zero. So usually a correlation is between two continuous ratio variables, one on the x-axis and one on the y-axis. And if you had person A, they would have a value for both variables. In this case, we have family income in thousands plotted against students' average grades. And you could see that person A has a family income of 31,000, and the student's average grade is 72. So you would come here and you'd look at 31 compared to 72, and this right here is the representation. This dot is the representation of person A for both variables. Person B is found at 38,086. So you'd come over here to 38,000 and up here to 86. That right there is person B. And every one of these plots right here, or every one of these individuals right here would be plotted in this graph in order to visualize the correlation or the relationship between these two variables. Now, correlations measure and describe the relationship between two continuous variables. Note the word correlation is actually pretty self-identifiable. The relation part of the word indicates that two things are have some kind of association with each other, some relation with each other. And the co part means together. So these two things are co-related. There are three parts of correlation. The direction, that's negative or positive, and is indicated by the sign, either a positive sign or a negative sign of the correlation coefficient. We will learn what that means later on, but when you see a positive correlation, it means that it's going up to the right. When you see a negative correlation, it's going down to the left. Now, we call this a positive correlation because both variables move in the same direction. If x is increasing, then y is increasing. So as values of x get bigger, values of y get bigger as well, and that's the reason why the tendency of the variables, the overall shape of the dots here, tends upward toward the right. In a negative correlation, the variables are inversely related to each other, so that as one gets bigger, the other gets smaller. So as this x, as the x variable gets larger, the y variable gets smaller. You can see that represented here, where high values on the x variable actually represent relatively low values on the y over here. So the first part of a correlation is the direction, whether it's positive or negative. The second component is the form. Linear is the most common and the only kind that we'll learn about in this class, but there are also nonlinear correlations like this. And thirdly, the strength or consistency of the correlation. And this value will vary from 0 to 1. So a strong correlation is where all of the points in the data set are clustered very closely together like this. A weak correlation is where they're spread further apart like this, and no correlation is where you can't discern any relationship between the dots on the x and the y variables. If you know what somebody gets on the x-axis, you will still have no idea what they'll get on the y-axis because they're all over the place. There's no obvious relationship. When you see something like this, a strong correlation, this will be near the value of 1. The strength of the correlation is reflected in its coefficient, and that coefficient number will be close to 1. Like if you observe this right here, this is probably like 0.8 or 0.9 as a correlation. A weak correlation will be closer to 0. This one right here will be probably something like 0.3 or 0.4. And if you see no correlation, then it literally is 0. So a correlation can range from 0 to 1, and because it can be either positive or negative, it actually varies from -1 to +1. But the strength or consistency, that component of it, that will range from 0 to 1. And when you include the sign, then it ranges from -1 to +1. These characteristics are all independent of each other. So you can have a positive correlation that's strong, or a positive correlation that's weak. You could have a negative correlation that's strong or weak. You could have a positive non-linear correlation. We're not going to really spend much time on these in this class, but the point is that you could have any combination of these different kinds of correlations here, because all these characteristics are independent. There are many kinds of correlations. They named them after the researchers who first developed the computations of them. There's like a point biserial, and Spearman, and a Pearson, and partial correlation. And for now, we're going to talk about the Pearson correlation. And this is indicated by the italicized letter R. In previous modules, we've encountered an italicized letter R, but we usually talk about it as R squared. This actually is the same R as the R squared, but it's just in the square-rooted form. The R correlation can range from -1 to +1, like I said, and if it lands at either -1 or +1, that indicates a perfect correlation, a perfect linear relationship. So as you see, every dot on this graph falls exactly on the same line. That indicates that all of these dots follow a particular perfect pattern, where if you were to kind of circle the overall pattern of this relationship, you would find that they're so tight that if you know a value on x, you do know exactly what the value will be on the y variable as well, because there's no variability away from that overall tendency to be on this line. So every change in x has a corresponding precise, exact change in y. And like I said, the correlation can be -1 if it's in this negative direction, or it could be +1 if it were in the upward direction. The instance when there is no relationship, as I said before on the last slide, is indicated by a correlation of 0, where a change in x does not correspond to any consistent change in y. If you see an increase in something on the x-axis, you don't know what's happening on the y-axis because there's no predictability here between the two variables. Now this R that I showed you here is computed as the covariability of x and y, how much they co-vary, and we divide that by the variability of x and y separately. So how much variability is there in the x variable? How much variability is there in the y variable? And if we consider both of those variables and the variability or the variance of them, then we can compare how much variability we would expect just by chance in each of these two variables. And then we would compare it against how much variability we see in the two variables together. And that allows us to say how much covariability there is in relation to how much variability there is when the two variables are considered separately, just because of random variability in the variables themselves. In order to compute this, we have to talk about a new statistic that we haven't addressed before. It's called the sum of products. This is similar to the sum of squares, which, as you know from many previous modules, is the sum of the squared deviations. We talked about this first in Module 2 when we took the distance between the score and the mean. And you remember that that distance is called a deviation score, and we square them. Those squared deviations added up for all the scores in a sample mean or equals the sum of squares. Whereas the sum of squares measures the variability in a single variable, the sum of products measures the amount of covariability between two variables. So you can see here the definitional formula. I'll show you in a minute the computational formula, but this is actually quite similar to the definitional formula of the sum of squares. Remember, the sum of squares is the distance between any given score and its mean squared. It would have a little 2 here to square it, and then we would sum them up. But instead of squaring these scores, we take the individual scores on the x variable and subtract from it the mean on that variable. And then we do the same thing with the other variable, the y variable. We take the scores on the other variable and we find the distance of them from the mean, so we compute other deviation scores. And instead of squaring these, we multiply the two different types together, which is very similar to squaring. In fact, if they were the same distance apart on both variables, you would expect for them to basically be the same as squaring. And then you add them up, and you call this the sum of products. So just to review, this is the deviation between each score and the mean in the first variable, the deviation between each score and the mean in the second variable, multiply them together, and then add them up. That's the method by which you compute the sum of products. Let's walk through an example of computing the sum of products using the definitional formula. Let's imagine that we had 4 people. 1, 2, 3, 4. These are also the scores for those same 4 people on another variable. 1, 2, 3, 4 people. Okay. These are the scores on the first variable. These are the scores on the second variable. It doesn't matter what these are. You can call them anything you want. One of the examples that we went through earlier was family's income and GPA, or but you could call them anything you want. It doesn't matter that they're 2 variables, each one being measured for all 4 people. So this row represents person A, this row represents person B, person C, and person D. Okay, so we can compute the mean of the x scores here and the mean of the y scores here. Recall that the first thing we need to do in the definitional formula of the sum of products is to find the deviation of each score from its mean. 1 minus 3 is negative 2. 2 minus 3 is negative 1. 4 minus 3, positive 1. 5 minus 3, positive 2. You can do the same thing for the y variable. 3 minus 5, negative 2. 6 minus 5, positive 1. 4 minus 5, negative 1. And 7 minus 5 is positive 2. So what we've done so far is found the deviation of how far each of these individual scores is from the mean of that set of scores. Then, to find the sum of products, we multiply together each of these times each of these. So negative 2 times negative 2 is 4. Negative 1 times positive 1 is negative 1. Positive 1 times negative 1 is negative 1. And positive 2 times positive 2 is 4. If you add those up, that's the sum of the products, or 6. Now the computational formula, just like when we when we used a computational formula for the sum of squares, is often easier to use and not as prone to calculation errors. And so we provide for you this computational formula, and you'll notice when you look at it that it follows a very similar format to the sum of squares computational formula. Instead of the sum of x squared minus the sum of x squared over n, it's the sum of x times y. And if these are similar to each other, then that would be almost the exact same thing as squaring them. And here we take the sum of x times the sum of y, and we divide it by n, just like we did in the computational formula of sum of squares. So, in this situation, we could imagine the same 4 people with the same scores as I showed you on the last slide. If you wanted to figure out this computational formula, you would multiply first x times y, right here. X times y, x times y, x times y. Okay, and then after you were done with that, you would sum up all of the x's. You'd add these up, they come to 12. You'd sum all the y's, add these up, they come to 20. And if you plugged in the component here, that's the sum of all the x times y's, 66. And you subtract from that the sum of the x's times the sum of the y's, you would end up with something that looks like this. You would divide it by the n size of this sample, which is 4. 4 people were in this sample. And you would calculate this through to 6, which is the same sum of products that we found using the definitional formula. In order to compute the R, remember that R is a ratio comparing the covariability of the two variables in the numerator with a combined estimate of the variability of x and y separately in the denominator. So we're comparing how much covariance we see between the two variables compared against or divided by the variability that we see in the two variables just individually considered. Just the variability in x and the variability in y. So that gives us an indication of how much variability we would expect just by chance, ignoring the co-relationship between the two. In statistical terms, that ends up being the sum of products, which is the an estimate of the covariability of the two, divided by an estimate of the variability of these two separately. And in order to combine them, we take the variability of the one separately from the other, and the variability of the other separate from the first. We multiply them together, and then take the square root, because, as you know, square rooting does this opposite thing of squaring. And if these are very similar to each other, then this would be almost the same as squaring. And so, when you square these together and take the square root, you're assessing the degree of variability in the two things separately. Let's walk through an example. Let's calculate the correlation, or the R, for the pairs of scores in these 5 people. So these 5 people here have a set of scores on 2 variables. This is person A, person B, person C, person D, person E. Okay, so if we plotted out all these numbers, you would see that the first person has a 0 on the x-axis and a 2 on the y-axis, so we would plot that person here. Person 2 has a 10 on the x and a 6 on the y. We would carry this over to 10 on the x and a 6 on the y. This is person B. And we plot all the other people. You would see that they follow a general relationship that looks something like this. If you circle it kind of like this, you can get an overall sense for the trend. You would see that this is probably a positive correlation because it seems upward leaning to the right. We could also make a guess about how strong a correlation we think this is. These seem modestly spread out along the group, and so we might say this is something like I don't know, 0.6 or something like that. 0.7 maybe, I don't know. All right, now let's go through the process of computing the R. Remember, we have the original scores here, just like in the table. In each case, we need to figure out what is the distance between the score and the mean of this group of scores. As you can see here, the mean of this group of scores is 6. So if we take 0 minus 6, it's negative 6. 10 minus 6 is 4. 4 minus 6 is negative 2. 8 minus 6 is positive 2. 8 minus 6 is positive 2. If we could compute the mean of this set of scores here, you'd see that it's 4. So if you take 2 minus 4, it's negative 2. 6 minus 4 is positive 2, and so forth. So what we've done so far is computed the deviation of each of these individual scores from the mean of that group of scores. In order to find the squared deviations, we would take each of these things and square it. So negative 6 times negative 6 is 36. 4 times 4 is 16. Negative 2 times negative 2 is 4. In order to find the squared deviations of the y variable, we square these. Negative 2 times negative 2 is 4. Positive 2 times positive 2 is 4. Negative 2 times negative 2 is 4, and so on. We would also find the products, which is the deviations of x times the deviations of y. So we would multiply these two values together. Negative 6 times negative 2 is positive 12. 4 times 2 is 8. Negative 2 times negative 2 is 4, and so forth. So now what we've done, if we add these up, and we add these up, and we add these up, is we have the sum of squares for x, the sum of squares for y, and the sum of the products. We can use those three values in computing the R, because the R is the sum of products over the combined variance of the two variables separately. If we plug those in, we take that SP down here and we put it at the top of the equation. And then we take 64 times 16 underneath this square root here. And if you carry this formula through, you get an R of 0.857. So as we estimated before, we thought it would be a positive correlation. It is indeed. We thought they'd be clustered pretty close together, and so it would be closer to 1 than to 0. And indeed, it was close to 1. It was 0.8. Now, correlations are useful for a lot of different kinds of things. They can be used in predictions. For instance, if you're given a value on one variable, you can make a guess about what the other one would be. In this example here, I've plotted SAT scores against first-year college GPA. That's actually what the point of an SAT score is. When you take an SAT, you're trying to demonstrate to college admissions advisors what you're likely to obtain as your GPA in the first year of your college experience. And SAT scores are pretty decent at predicting that. And so you'd see that generally, the higher you do on the SAT, the higher your GPA is the first year of college. It's not a perfect correlation, but it is pretty strong. So prediction is one use of correlations. If you know one variable, you can guess what somebody will get on the other. Another use of correlations is validating measures, in which case scores on an established measure should be related to the scores on a new measure. Here, I'm using the same example data, but I'm relabeling the axes for an example that is near and dear to my heart. My focus area in the field of psychology is on the psychology of religion. And there is an old scale that measures people's questing, their seeking of religion, their desire to understand more and to explore the issues of religion and search out God. This is an old measure that was developed way back in like the 50s or something like that. But there's a new measure that's called the CROI. That stands for the Circumflex Religiosity Orientation Inventory. And the CROI measures a lot of different components, but one of those things is kind of seeking behavior. And you'd expect that if this new measure of seeking behavior in religious contexts is a good measure, that it should be related to the old measure of quest. And so you could use a correlation to validate the new measure, CROI, using scores on the old quest inventory. So if I gave people both the quest survey and the CROI survey, then they should get similar scores on both. Not exactly the same, but if they score high on the quest, they should score high on the CROI, and if they score low on the quest, they should score low on the CROI. A third use of correlations is reliability. In this case, we'll use the example of extroversion scores on a survey last week compared to extroversion scores today. You would expect that this measure should be the same this week as it was last week. And if you find that they are, it might not be exactly the same, but if they're closely related to each other, then you can say that this survey that we're using to measure extroversion is reliable. It's the kind of survey that if you administer today and next week, you'll get similar results both times. It's reliable over time. And finally, you can use it for theory validation or verification. And in this case, you could see the example of smoking and lung cancer. If you're smoking more often, then you're more likely to get lung cancer. We never have been able to do experimental studies about smoking to see the impact because it's unethical to force somebody to smoke and to force other people not to in an experimental situation. So rather what we do is hundreds and hundreds of studies where we measure smoking and other kinds of things, and if we see reliable, consistent relationships, then we validate our theory that those two things are related to each other. However, we need to be cautious when we're interpreting correlations because although it's useful for those four things, it does not demonstrate causation. Just because two things are related to each other does not mean that one of those things caused the other one. Now, there may be a causal relationship, like we talked about in the case of cigarette smoking and heart disease or lung cancer, but it may also not be a causal relationship. If you look at this map right here, you'll see that the number of churches is correlated with the number of serious crimes. Now, are churches causing serious crimes? Probably not. Rather, a larger population probably causes both the growth in the number of churches and the number of serious crimes. So if you live in a larger area with more people, then you're going to have more churches, but you're also going to have more crimes because you've just got more people. Thus, establishing causation requires an experiment in which one variable is manipulated by the experimenter, by the researcher, and then other variables are carefully controlled. Often that's in a laboratory situation where all of the variables are kept constant. Everything's the same except for the only one thing that you've manipulated, the one thing that you've changed. And then, if scores are different across the two conditions, then you know that the reason for the difference is because of the one thing you've changed. And you can say that the thing you've changed, the independent variable you manipulated, is the cause of any differences you observe in the dependent variable. Another caution that we need to understand about correlations is that if we're using a restricted range of scores, we can't really draw generalized conclusions. The size of the correlation coefficient is going to be affected by the range of the scores that we have measured in our data. A severely restricted range may provide a very different correlation than would a broader range of scores. For example, if you only surveyed college students, then you might see that there's no relationship between IQ scores and creativity. As you can see here, we have just what looks to be no relationship at all. But the reason for this is because our x values here on this axis are restricted to just this limited range of college students who are brighter than the typical person in the population. They might have IQ scores higher than the average, maybe something ranging between 110 and 130. And all the levels of creativity here are restricted as well because of that. However, if we include other people with lower IQ scores who are not college students, and we thus have like IQ scores ranging from 70 to 130, as the population generally does, then you might see that there is a correlation between IQ and creativity. So, in order to be safe, we should never generalize a correlation beyond the sample range of data. So if we said here there's no correlation, we should be specific in saying that there's no correlation when we restrict our range to the IQ scores of around 110 to 130, or when we're just measuring college students. But if we were to measure more people with lower IQs who were not college students, it's quite possible that there would be a correlation. So we have to hedge our bets whenever we draw a conclusion if we've restricted the range of our sample data. An outlier in a data set is often extremely deviant and can disproportionately impact our correlation coefficient. So as you see here, this is a sample of 5 scores, and if you circle them, you can see that this doesn't really show any general trend. It seems to be no correlation. And if you compute the R value for this set of 5 data points, then you'll see that it's almost exactly 0. It's a tiny bit away from 0, but it's basically 0, indicating no correlation. If we add in one additional outlier up here, these original 5 scores now, in relation to this one, appear to have a very strong correlation. And if you compute the R, it indicates indeed that there is a strong correlation here. 0.8 is really close to 1, which means that these values fall very tightly clustered around a particular trend of data. This overall tendency looks to be a strong positive correlation. But really, this one data point is the whole cause of this correlation. It's not actually a strong correlation. When you look at these 5 data points alone, they're not correlated, but one outlier can strongly influence a correlation, especially if the sample size is small. Thus, when you have an outlier in your sample, you have to be very cautious about interpreting your correlation as significant or as being a meaningful, reliable correlation. Now, as I've said before, a correlation coefficient measures the degree of relationship on a scale from 0 to 1. But because of that, it's easy to mistakenly interpret that this decimal point is a percentage or a proportion. But it's not. It's not a proportion or a percentage, so don't interpret it like that. Just recognize that what it means is, if you have a correlation of 0, it means no correlation. And the correlation of 1 means a perfect correlation. And anything between these values indicates weaker or stronger depending on where it falls in this range. That said, because the correlation is indicated by this letter R, if we square it, then we can interpret a squared correlation as the proportion of shared variability between the two variables. So if you take this R and you square it, whatever this R value is, and square it, then you can interpret that value as the proportion or the percentage of variability that's accounted for by the relationship between the two variables. So it's the percentage of variance accounted for by the two variables together, the shared relationship of the two variables. Here's an example. If you have IQ and college GPA, these two variables have a correlation of about R of 0.6. If you square that, that equals 0.36. So R squared, just like we saw in previous modules where we've used it to account for where we've used it to represent a percentage of variability accounted for, you can say the same thing here. This right here is a modest positive correlation. It's not perfect. In fact, only about 36% of the variance in GPA scores can be accounted for by IQ scores. So I'll say it a different way. About 36% of the differences found in your GPA can be predicted by or accounted for by what your IQ score is. IQ scores predict about 36% of the differences or variability in your college GPA. So if you're relatively smarter, then you might have relatively higher GPAs. But there's a lot of other things that can impact GPA. The rest of the variability, the other, 67%, no, 64%. The rest of that variability might be due to how hard the students work, their average course load per term, whether they also have a job, whether they can afford a tutor, whether they do their homework, etc. So lots of things can impact your GPA, not just your intelligence. But intelligence definitely plays a role. How much of a role? About 36% of the differences that you see in GPA are because of intelligence, but the rest is because of other stuff. Now that we understand how to compute the R, let's walk through the process of computing a hypothesis test using the Pearson correlation. A Pearson correlation is usually computed on sample data, but we use it to test hypotheses about relationships between two variables in the population. We don't actually care about the 5 or 15 or 30 people that are in our sample. We don't care if GPAs and IQ are related just in those few folks. We care that GPA and IQ are related in the population, among all the students, among everybody. And so when we gather a sample and we compute an R on that sample data, what we're trying to do is say if there is or isn't a relationship between these two variables in the population. Now, a population correlation coefficient isn't indicated by the letter R. It's shown by the Greek letter rho, or this italicized P-looking thing. But this is pronounced rho. Remember, this is similar to the fact that if you compute a mean of a sample, the population mean isn't indicated by an italicized M, it's indicated by an italicized mu. In this case, the letter rho is the Greek equivalent of our letter R, and so we use this in place of R when we're talking about the population. So if we're doing a non-directional hypothesis test, then we would say the null hypothesis is that the correlation in the population is nothing. There is none. The two variables are not related to each other. And the alternative hypothesis is the opposite of that the correlation is something other than zero, that there is a relationship in the population between those two variables. There is a correlation. Alternatively, if we were using a directional hypothesis test, where we hypothesized or guessed that the relationship was positive in the population, then we would say first, remember we always start with the alternative hypothesis first if we're using a directional hypothesis test. So we'd say the alternative hypothesis is that there is a correlation greater than zero. If there was a positive correlation, that's what we would guess. In which case, the null hypothesis would be that the correlation is the opposite of this. Instead of being greater than, we would say it's less than or equal to zero. Something less than zero. If we were hypothesizing a negative correlation, then we would say that the alternative hypothesis is the correlation in the population is less than zero. It's something negative, something less than zero. And in that case, we would write the null hypothesis as the correlation is something greater than or equal to zero. Now, even if there is no correlation in the population, a sample can make it seem like there is one, especially if there are small samples. So let's imagine that we drew these 3 points out of this population of scores. in the population, you can see there is actually no correlation. But if we drew only those 3 points, it would look almost like there was a correlation. In fact, it would be a modestly positive correlation. Because of that principle, we have to take a correlation R, computed from the sample, and test something about the population rho, and make a guess to say whether the sample is suggesting there's truly a correlation in the population or not. If your R that you compute is not exactly 0, like we saw in this example, it's not 0, and indeed it almost never is exactly 0, then you have to decide which one of these example statements is true. Either there is no correlation in the population, like this, there is no correlation in the population, and your non-zero R is actually the result of sampling error. It just looks like there's a correlation, even though there's really not a correlation in the population. Or, if you gather sample data like this, remember, you don't actually know what the population looks like, so given these sample data, it might be that the population actually has a correlation that looks like this, and these 3 data points reflect this population of scores. And that non-zero R coefficient accurately reflects that case, that there really is a correlation in the population, which is the alternative hypothesis. In order to make the guess about whether this sample reflects a population where there's no correlation or a population where there is a correlation, we have to be able to compare the strength of the covariability between these 2 variables here against how much variability is in each of the variables by itself. And remember, we pit those 2 against each other. The first goes on the top of the equation, and the second goes on the bottom of that fraction. And when we pit them against each other, that allows us to see how much of a relationship there is between these variables together versus each of the variables separately. When we run a hypothesis test on a correlation, the degrees of freedom is n-2. Now that might surprise you because always before it's been n-1, except in one module for a very specific reason. So why is it n-2 in this situation? If you only have 2 data points, they will make a perfect correlation of 1 every time. You see how there's only one line that can be drawn between these 2 data points, which means that all of the data points necessarily, invariably, always fall perfectly on the line. So it always has a correlation of 1. So the sample correlation is only free to vary something different than 1 if there are more than 2 points. So the first 2 points are not free to vary. After that, your points are more free to vary, and you can have correlations that are different from 1. And so we take away the first 2, and we say that the degrees of freedom is everything less than, is everything else other than those 2, so n-2. Now let's walk through a correlation hypothesis test. The critical values for the R are listed in table B.6. That table looks like this. The degrees of freedom are listed in the far left column of the table, and you can find the degrees of freedom that are associated with your scenario here. And then you have to decide what your level of significance for the two-tailed test is. There's actually another another row of headings above this in the table, but I didn't show it in this slide, that show the significance values for a one-tailed test. But usually you will use a two-tailed test, and your scores will correspond to alpha levels of 0.05 or 0.01. It might be something else, but usually 0.05 or 0.01. So let's go through an example. A researcher wants to know whether there is any relationship between income and happiness. She collects data from a sample of 30 people and obtains a correlation coefficient of R equals 0.35. Using an alpha of 0.05, is this correlation significant? Now the way we know is to look in our table. Degrees of freedom is n minus 2, so 30 minus 2 is 28. We come down here to 28, that's the very bottom of the table, at least in this particular image, because I've shortened it. And then we go across to our alpha of 0.05, which is right here, 0.361. And this is our critical R. This is the R against which we have to compare our obtained R. If the R we got is bigger than this, that means it's significant in the population. And if it's smaller than this, then we say it's too small to conclude that there's a real correlation here. It's probably just a correlation that appears to be bigger than 0 just by chance. But this is the value against which we think a correlation needs to be bigger than this value if it's going to have an actual correlation in the population. The correlation we computed was 0.35. It's not bigger than 0.361, so we say this correlation is not different enough from 0 to be called a real correlation, a significant correlation. Instead, we have to conclude that this is pretty much no correlation. So the answer is no, there's not a significant correlation because the critical R is 0.361 and our correlation is not bigger than that. Imagine instead that the researcher had started out wanting to know whether there is a positive correlation between income and happiness. Would this same correlation have been significant? I didn't copy over the top heading that indicates the one-tailed test, but the one-tailed significance level of 0.05 appears above this column here. So you'd follow this down to the same level at 28 as the degrees of freedom, and you would use this critical value for your R instead. And then you could answer the question, does that R of 0.35 that we computed look bigger than this? And if it does, then we say, yes, we can call this a significant correlation because the critical R was 0.306. The one we calculated was 0.35. It's bigger than that, so we say, yes, we reject the null hypothesis. It's sufficiently different from 0. In literature, we report whether a correlation is statistically significant, as well as the value of the correlation, the sample size, the p-level, or the exact value, if you used a computer and it told you what the exact p-value was, and the type of test that you performed if it was one-tailed. So an example might look like this. A correlation for the data revealed a significant relationship between annual income and happiness, comma, R equals 0.35, comma, N equals 30, comma, P less than 0.05, comma, one-tailed. In all of our previous statistical reporting, we have reported the degrees of freedom in parentheses right here. Notice that that's not the case in this example. We're going to report the n size instead. And we're going to, again, give the p-value just like we have been for a long time, right after the statistic. Now, if you have more than 2 variables that you're computing the correlation for, most studies report these values in what's called a correlation matrix. We put the values inside this table where the variables that you're correlating together fall along the rows and also along the columns. So you might start your sentence something like, the analysis examined the relationships among income, amount of education, age, and intelligence for 30 participants. The correlations between pairs of variables are reported in Table 1, and significant correlations are noted in the table. So when you correlate income compared to income, you're always going to find that they're perfectly related, because somebody's own value on income is exactly the same as their own same value on income. Now, that's kind of nonsensical, so we sometimes put this 1 here to indicate that it's a perfect correlation, but sometimes we don't bother putting that value there. Sometimes we just leave it out. When you relate somebody's income and education together, it might have a value of whatever that is, 0.65. That's a modest correlation, but the stars next to it indicate its level of significance. In the key over here, you can see that 2 stars means that it was significant at the 0.01 level in the two-tailed test. Here, we see that the relationship between income and age is 0.41, slightly smaller and also less significant because this is only significant at the 0.05 level. The relationship between education and age is not actually significant at all. It's so small, 0.11, that it's not even considered different from 0. When we did the hypothesis test for this one, we didn't find that it was less than 0.05, so it doesn't get a star, and that means that it's not a significant correlation. When you put these in a correlation matrix like this, you usually leave the underside of the correlation matrix blank, or you could put them on the underside and leave the upper side blank, but you don't put them in both cells because it would be redundant to list 0.65 in this cell, like education and income here, as well as education and income here, because it's the same value. And so in order to not be redundant, we just put them either in the upper half of the table or in the lower half of the table, but not both. Now that we've described a Pearson correlation, I want to introduce you briefly to a second type of correlation called the partial correlation. I'm going to show you the formula for this, but I am also going to warn you up front that I'll never make you compute this. It's a little complicated and it's unnecessary that you understand exactly how the mathematics works. Mostly what I want you to understand instead is how it conceptually works. So a partial correlation measures the relationship between 2 variables while mathematically controlling for the influence of a third variable by holding it constant. One example is there still a correlation between the number of churches in an area and serious crimes in that area when we hold population constant? So in this example, we've got a number of churches here on the x-axis and a number of crimes on the y-axis, and you see there's a positive correlation between them. But we've also got small cities down here, medium cities here, and large cities up here. If you have 3 variables, you can compute 3 different correlations from them. You can compute the correlation between x and y, the correlation between x and z, and the correlation between y and z. Once you've computed those 3 correlations, then you can use those different correlations in this formula to compute the correlation for 2 variables, x and y, right here, while holding a third variable constant. So, in this example, the correlation between churches and crime is 0.92. The correlation between churches and population is 0.96. And the correlation between the final 2, crime and population, is 0.96. So, is there a relationship between the number of churches and the number of crimes when you hold the population constant? You take these 3 correlation values and put them into this formula here, and if you carry it through, the value is 0, meaning there is no correlation between x and y, between churches and crimes, if you take out z, the population. If you mathematically remove that variability, there is no more correlation left between x and y. Visually, what's going on is, remember we had our small cities, medium cities, and large cities. Basically, we're mathematically forcing all of those cities to overlap with each other and be treated as if they were medium cities. So we've held constant all of the different sizes of cities and we've made them as if they were equivalent. And then we ask the question, is there a correlation now once we've removed the size of the cities to make them all approximately the same size? And the answer, of course, is no, there's no correlation between number of churches and number of crimes when you hold constant the effect of population. Another way you can use partial correlation is to demonstrate that there still is a relationship even after you remove the influence of a third variable that's a potential confounding variable. So you could use the partial correlation to rule out other explanations for a relationship. For instance, one researcher surveyed about 1,800 adolescents between the ages of 12 and 17 and found that the more sexual behavior they observed in television, the more likely they were to engage in sexual behavior. But the researchers wanted to know, was this merely due to age? Because presumably, as adolescents get older, they're more likely to see increasing amounts of sexual behavior in television. And so they thought, well, as they get older, they'll probably have seen more sexual behavior, but they'll also be older and therefore more likely to engage in sexual behavior. So are both of these changes in increase caused by actual age differences rather than any relationship between watching sex on television and engaging in sexual behaviors? And using a partial correlation, they held age constant. Doing so, they found that the relationship between viewing sexual content and the amount of sexual behavior that they engaged in remained. So they could say, it's not actually caused by age. This relationship between viewing sexual content on TV and engaging in actual sexual acts is still a valid correlation. It's still a relationship. Those two things are still related to each other, even when we control for age. So, before you finish this module, I want you to take a minute and walk through this practice exercise. It's just computing a Pearson correlation, going through the hypothesis test, and writing a sentence as if for publication. So here, we have a researcher who asks people their grades and how many books they've read for leisure in the past 12 months. Here you've got respondents 1 through 5 listed, with the number of books they've read and their GPA scores. I want you to calculate the correlation coefficient and run a hypothesis test to see if it is statistically significant. You should use a two-tailed alpha of 0.05 and then write a sentence as if for publication. Pause your video, and when you're ready to see the answers, resume. Okay, if you use the SP formula that's computational, you should have been able to ascertain that following the equation through, you get 9.3. You can use that 9.3 in your R formula here. So then you divide it by the sum of squares of x times the sum of squares of y, take the square root of that. If you pit those against each other, it carries out to 0.959. That's a very large correlation, very strong. Our data suggests there is a significant correlation between the number of books a person has read in the past year and their GPA, comma R equals 0.959, P less than 0.05, N equals 5. And the reason why we could conclude that this is significant is because our correlation was larger than the critical R, and that critical R in the table was 0.878. Therefore, it's significant.